Section 6, we're going to look at something called Avogadro's law. Well, you recognize that name, of course, from Avogadro's number, 6.02 times 10 to the 23 pieces is equal to 1 mole. Well, I believe I mentioned back when we covered that, Avogadro didn't actually know his number when he was alive. He had a theory about different things being equal, and later on it was proved that, yeah, it was true, and so the number was named in honor of him. His theory came from this idea right here, that if you had some container of gas, the textbook here has chosen to go with basketballs. They've got kind of a fixed volume, so it makes sense there. I tend to think of balloons myself, but that if you have a balloon, and say this balloon has helium gas in it, and this balloon here, which I'm going to try to draw the same, that's horrible, but we're going to pretend. Let's say that one I inflated with my breath, and even though your breath is mostly nitrogen, I will label it as carbon dioxide there. And then we have one that is, say, a mixture of gases, and again, we're going to pretend that's the same size, and that is just air. Well, it turns out that if they all have the same volume, that if the volume of helium is equal to the volume of the CO2 is equal to the volume of the air, that they all have then the same number of pieces, the same moles. Now they're going to have different masses because each of those gases, helium has a molar mass of 4 grams per mole. Carbon dioxide, it's like 44.01 grams per mole. And air, you got to factor in all the different pieces, but it's around 29 grams per mole, depending on humidity. Interestingly, even though we talk about the air being heavy when it's really humid, water has a molar mass of 18.016. If we're picky, I think the periodic tables we've been using it rounds to 18.02, but that's grams per mole as well. It is less dense than the density of air. And so then because of that, the air is actually less dense when there's a lot of water vapor in the air. And the reason it feels heavy has to do with how your body reacts to the increased warmth that comes with high humidity, what's called the heat index, and not with the actual density of the air changing. His theory was that it was the same number of pieces. And it turns out it was a good theory, it's a good idea. And so that is Avogadro's law. In Avogadro's law, we're finally going to see a relationship where we don't hold the number of pieces of gas constant, but we change the amount of gas. This one should be obvious. If I have a container, and if I want to keep pressure and temperature constant, I've got to take off the cap that I've had on this before. Well, I've got a certain amount of gas in here. If I increase the volume, it's going to draw more gas in there, and now there's more gas in there. That is exactly what Avogadro's law. It's super obvious. I have gas in there. If I give myself more space, I can fit more gas in there. There's more gas in there. But as it mentioned on that first slide, and doesn't actually have here again, the volume of 1 mole of any gas is 22.4 liters. As a side note, I was taught to memorize 22.414, which is a little bit more accurate. Because of that, if you hear me slip into that, you'll know why. But your textbook, we're going to use 22.4 and just round it off a little bit more. But you'll notice if we have two things that are equal, well, now we have two conversion factors where we can put moles of a gas over liters of gas, or liters of a gas over moles of a gas. As we've had before, the number that goes with moles is always 1, and here the liters for a gas is 22.4 liters. Now, this is at constant temperature and pressure. It's technically at something called STP, standard temperature and pressure. And what it is we've just agreed that if we're going to compare gases, that we're going to do it at a particular temperature to particular pressure. And that will come up here on a slide in just a moment. So here we're told a number of moles initially of helium gas and a volume initially, and then we're going to ask what the volume final will be when we increase the number of moles to be more. And we're holding temperature and pressure constant, of course. Well, we're just going to use the Avogadro's law formula there. Volume initial over number of moles initial is equal to volume final over number of moles final. and then it's just plug in the numbers. So 1.5 liters over 0.75 moles is equal to volume final over 1.2 moles. Volume final then is going to equal 1.5 liters times 1.2 moles divided by 0.75 moles. Again, I kind of skipped an algebra step in my head there. Cancel out the mole units and we're left with liters, which makes sense for our volume. And let's see here, the amount of gas went up, and so then I'd expect the volume to go up because these two are a direct relationship. And so then our volume final is equal to 2.4 liters, which is choice C here. And that makes sense for what we just predicted, that the volume is going to go up. As I mentioned, we're going to do these things at standard temperature and pressure. That is something called STP. Standard temperature is 0 degrees Celsius or 273 Kelvin. That is cold. 0 Celsius is 32 degrees Fahrenheit, recall. And so that's just what we've agreed. Most labs are not at that. That is low for most labs, of course. Most labs are probably at around 20 degrees Celsius or 293 Kelvin, which is around 70 degrees Fahrenheit, and that means we have to do a conversion. We have to use the gas laws to convert, okay, what would it be at STP so that we know how many moles we have. And then standard pressure is 1 atmosphere or the 760 millimeters of mercury or the 101.3 kilopascals, the 7760 torr, as well as all those other gas units that you saw previously. We're going to tend to work with just these three here, so we'll leave it at that. I've mentioned already that we have the conversion factors. If you want to take a moment and read the details there, you can. And I did the balloon analogy on the first slide. I use different gases, but notice they start with helium, and then instead of carbon dioxide, they have oxygen, and instead of air, they have nitrogen, which you'll notice the density of air that I gave you is really close to the density of nitrogen there, the mass of nitrogen, because nitrogen is the main component of our air, and the other pieces, the oxygen and carbon dioxide, raise its density a little bit. The water vapor lowers a little bit. The argon, I don't recall its molar mass, but I think it lowers it a little bit as well. And yet, despite having different masses, they're all at the same temperature, they're all at the same pressure, and so then they all have the same number of pieces and take up the same volume, because we assume the gas particles inside of there themselves are volumeless, that they're so tiny and they don't really significantly interact with one another, are properties of an ideal gas or the kinetic molecular theory. So here we're going to use that conversion factor. We have number of moles, and we're asked what is the volume. Well, you'll notice we can't use Avogadro's law here because we're not given two different conditions. We're given just one. So we're going to start out with 2.75 moles of nitrogen. We're told it's at STP, and so then because of that, we can turn moles of nitrogen into liters of nitrogen, because any 1 mole of a gas, any gas, has 22.4 liters. And when you do that, you get 61.6 liters of nitrogen gas. And since we have more than 1 mole, I'd expect my volume to be greater than 22 liters. As a side note, this molar volume of a gas that is 22 liters, I think of a 2-liter pop bottle. And it takes about 10 2-liter pop bottles to get to your 22. And so if you imagine 10 2-liters of pop bottles, that's literally how big these balloons would have to be to actually have 1 mole in them. It'd be huge balloons here. Now, you may be thinking to yourself, wait a second, 2-liter pop bottle, that should be 11 pop bottles. Well, it turns out that with that headspace up at the top, that headspace across 10 bottles is almost 2 liters as well. So you can get away with just 10 2-liter pop bottles being 1 mole of a gas. Well, if that was all helium gas, we had them sealed because obviously it'd want to raise up out of there. It only weigh 4 grams. The bottles obviously weigh way more than that, have a mass much higher, but there's not a lot of mass to gas. It takes a lot of gas to have any significant mass. That should make sense. Gas is lightweight. Wrapping up with just a couple more calculations here. This time we're given grams. Well, we haven't worked with grams of gases yet, but we've done grams before, and anytime you have grams, you should think to yourself, I need to get that into moles. So grams of CH4, and so then grams of CH4 and 1 mole of CH4. I'm going to need to use the molar mass. Well, it's 12.01 times 1 for the carbon, plus 1.01 times 4 for the hydrogen gas, and that is grams, and so that comes out to be 16.05 grams per mole. And then we're asked for volume, and so we can turn moles of any gas, 1 mole of this time methane gas, into 22.4 liters of methane gas. And that's going to come out to be 5.60 liters, which is A. This one here, we are doing 8 liters, so we're starting at the liters part of helium. We can turn liters into moles of helium is 22.4, and then we know the molar mass. 1 mole of helium has a mass of 4 grams of helium. 8 liters is going to be less than 1 mole. I'm going to expect a mass that's low here, 1.43 grams of helium, which is going to be choice C there. And that finishes up section 6.